So, time to get into numerical measures describing data sets. We kind of did that with the distribution tables, but now we're going to come up with single numbers that describe different characteristics of a data set. Okay? If I can get my slide to change. There we go. So, we usually look at two different main measures for describing characteristics of a population or of any data set. We want measures of location, like where is the data centered, where is, what is the cutoff for 25% of the observations, things like that. And then, of course, measures of variability, or how the data spreads out over its whole range. Okay? How much of it is close to the center? How much is far away? Do we have outliers? Things like that. Okay, so we're going to build those kinds of things. As stated in the intro material, remember we need to keep track of whether the data is from a population of interest or if it's just a sample from a population of interest, because now we're going to see that calculating some of these summary measures is actually different depending on whether the data is sample data or population data. And remember, what we're calculating is population parameters. Parameters state state the value of some characteristic of the population. Okay, like the average from the population, average income, average height, whatever it is, average age. Whereas if we take a sample and calculate the same things, those are called statistics. Statistics are estimates of parameters. Okay, sample statistics are estimates of population parameters. And in fact, the single value is a point estimator. It's estimating a single value in the population. So it's a point estimator. As we'll see later, point estimators aren't really the best estimates. So we usually have to create what's called an interval estimate, so a range that we think contains the truth. But we need probability to do that. So let's get these descriptive statistics, summary measures put together. Excuse me. And then we'll get into some probability stuff. And then next week we'll get into putting together probability distributions that we can do a whole lot more with and create interval estimates with. So it'll be a while before we get to those interval estimates, but we're well on the way here. Okay, so what are some measures of location? The mean is one, right? That tells us it's a mathematical measure of the center of the distribution. Okay, and we'll have a function for that. Median, also another measure of what's called central location, the center of the distribution. And sometimes these two agree with each other. They come up with the same number. Requires a certain property for the data set, but we'll get to that. Excuse me. Sometimes they don't agree at all. And in fact, whether the mean is above or below the median also will tell us something about the data set. Again, we'll get to that later. The mode is the most common observation in the data set. That's really not a very useful number. I've never seen it used for anything useful other than saying, well, here's the most common value in the distribution. Whether that has worth or not, I don't think so. Anyway, we'll talk about it, calculate it. Excel will calculate for us, and we won't do much else. Okay, many books call the mode a measure of central location too. I disagree. It is if we have a single peak and it agrees with the median and mean, which sometimes it can, but that's pretty rare. And most distributions, well, many distributions I should say, may have more than one mode, and it may not be anywhere near the center. So anyway, and then this last piece is our measures of non-central location. Okay, oops, sorry about that. And those are percentiles, quartiles, things I mentioned before. The 25% cutoff. So there's 4 quartiles in the data set. You're splitting it into, quarters. First 25%, second 25%, third, fourth. Percentiles is splitting it into tenths. Right? So first percentile is the first 10% of the data values in an ordered array. Anyway, so let's move on to formulas. Okay, so here's the mean or arithmetic average, or just the average, from a population data set. So we can calculate it using this formula, okay, which is a shorthand way of saying this. Okay, so remember this we see in Excel. Oh, I don't have my Excel open. I don't know what happened there. I called it the Riemann sum in an earlier lecture. At least I think I did. I should have if I didn't. So we have the Riemann sum up here. Same symbol. But it's called the Riemann sum. And all that's saying is, well, first let me point out, note we have a Greek letter here, and all our parameter values, characteristics of a population, all our parameter measures are typically used or denoted using a Greek letter. So this is the Greek letter mu, common across all statistics books and everything in statistics. Mu typically means the population parameter for the mean, the population mean. Okay, not a statistic. It's not a statistic. It's a parameter because it's about the population. So anyway, calculating this is adding up all the observations you want the mean for. So observation 1, x1, x2. So these are the observation values, summing up all the observation values and dividing by the sample size, or I should say population size. Sorry, it's not a sample; it's population. That's why it's a big N. So that's what this is shorthand for. So I know math symbols can be kind of confusing, but they're really just shorthand ways of saying something else. So rather than writing this out, we have this nice little Riemann sum symbol, and we divide the sum of the x sub I, going from I equals 1, observation 1, to n, size of the population, and then dividing it by that size of the population. Okay, hopefully that makes sense. And then for a statistic, if we have a sample of data and we want the average from that, note, no Greek letter here. We call it x bar. It's a sample statistic. It's a sample mean of a sample of data. Formula happens to be the same in this case. Okay, so there's no difference in the way you calculate it, but how they're denoted. Population parameter, the mean is mu. Sample statistic, the mean is x bar. That's what we call it, x bar. Weird, but it's common across all textbooks, used all the time by professionals. So if they say x bar equals this, you know it's the sample mean. If they say mu equals that, that's the parameter, population mean for whatever data they're talking about. Okay, so the only difference in the formula is here I have sample size, little n, here I have big N for population size, but really, same thing as far as calculating. And so the sample mean is a point estimator of the population mean. Right? We get a sample, we calculate its mean, we have an estimate of mu, the population parameter. So let's do a quick example of doing that by hand, sort of. So here we have an 11 observation data set, ranges from 0 to 10, and this is an ordered array of that data. Who knows what it is? So calculate the sample mean. It's a sample of data. So we're going to calculate sample mean. So here's our observations. Observation 4 is a 3, right? X4 is 3. X2 is 2. X11 is 10. So So we're going to sum those observation values up. From 1 to 11, we get a sum of 55. And then we need to divide by sample size, which is 11. So it turns out the mean here is 5. The average of this data is 5, whatever the data is. Okay, so pretty easy to calculate, especially for a small data set. You could do it by hand on, in your head probably. Just add up these numbers, divide them by sample size. Okay? So hopefully that makes sense. Pretty straightforward. So notice it is a mathematical equation we use to calculate this, and some characteristics. The mean depends on all of the values of the data. So remember I called it a measure of central location. It's telling us the data is centered on 5 using that measure. And actually that makes sense in this case because we can see all the data. 5 is actually right in the middle. So, 6th observation is 5. There's 5 below it, 5 observations on the other side, or I shouldn't say 5 below it. There's 5 observations to the left, 5 observations to the right, so that does happen to be right in the center here. However, if you have outliers, which just means we have an observation way far away from the center, on one side or the other, or maybe even both sides, that can screw up your mean. Okay, so let's say I have, instead of 10 being my highest value, I have 21. The rest of the data is all the same, kind of clustered around that 5 somewhat, but I have this high value on the right side. Now what happens if we calculate the mean? Well, now it sums up to 66, divide by 11, we get a sample mean of 6. Okay, so that's higher than it was before. That's putting the center of the distribution here, which clearly is not the center of the distribution. Okay? So the mean is affected, since we're actually using the data itself to calculate it. The mean can be affected by outliers, pretty dramatically, as we're seeing here. Right? Means here, not really the center of the data set. That's why we have alternative measures if you have outliers or if skewed data that stretches more in one direction than the other. Okay, so we'll do more with that later. But good thing to keep in mind, the mean isn't always the best measure of center to use. It depends on the data and how it spreads out. Okay, so I posted this data set. We have some apartment rents. We'll do some more stuff with it later. I don't think you need to worry about it today. Okay, so this is not an ordered array. What I posted is an ordered array. I just put it into a column, I think. So what we have is prices of apartments in some college town. Okay. Efficiency apartments. We have 70 observations. Here's our sample data. There's more than 70 efficiency apartments in this town, apparently. But we took a sample of 70 of them. So if we add all these up, divide by 70, here's our average. So the average rent on an efficiency apartment in this town is $490.80. Not bad. Must be old data, like most of my data. So that's the sample mean, right? I'm just applying the formula. Later we'll do it in Excel, but for now we'll just go with that. So here's a useful measure that we'll use later. Once we have a mean, either a sample mean or a population mean, we'll mostly be using samples. That's why I'm using those for examples. We can calculate these residuals, also known as deviations from the mean. We'll use this a lot when we get to the inferential statistics. Okay, and all that is the distance from the mean of each observation. We can calculate its distance from the mean. Okay, so that's what we have here. Xi, observation I minus the mean is its distance. So of course, if it's smaller than the mean, that means it's to the left of the mean, we'll get a negative number. So many units to the left of the mean would be the residual. Okay, so it's just deviation from the mean, or distance from the mean. Very useful concept, because we'll use that a lot. Deviation from the mean. We'll be measuring things in distance later. So let's calculate the deviation from the mean for each of the observations in the data set. Okay, so, oops, sorry. So we know the mean of the data, $490.80, average rent for efficiency apartments. So here I'm taking that table and calculating the deviation from the mean for each observation. So I just did this. Somewhere I'm going to have you do it in Excel. Why don't we do it now? Oh, shoot, I forgot about the weighted average. So here I have the average. Calculated all the deviations from the mean. Let's do that with the apartment rents data. I posted it. Apparently I didn't save the one I posted. I mean, I don't have that accessible, but I have it here. Give me a sec. You can download it. I did post it. Sample. So it's the name of what I posted is sample of apartment rents raw, the raw data, and I left all this in there. So we want to first calculate what's called the deviation from the mean, but before we can do that, we need to know the mean, right? So here I have a list of things we can calculate called descriptive statistics. So this is sample data, so these are descriptive statistics. Summary measures of the data set. We're not going to do them all right now, but we do need the mean. So I already gave it to you. We know it's $490 something, $490 and something, but let's calculate it. We already know how to do this. Well, I guess not. We did use the auto sum, but I showed you that the drop-down menu here has the average in it. Since the formula is essentially the same for population or sample data, we'll just use that. Okay, so click on that, brings up the function. Make it a little, whoops. And we want column A. So you can select the whole column with this function. So we want the average of the apartment rents. Of course, make sure there's nothing below the data. You know, if I threw a 15,000 something in there, that's going to really mess up my average, right? So you want to make sure there's nothing below the data you want to calculate on. Okay, and then we want deviation from the mean. Okay, so remember that's xi minus x bar. So all we've got to do is type that in, right? Equals the data value minus the sample mean. Now we want the data value to change as we move the formula, but again we want a constant reference to this sample mean. Okay, so remember we need to hit F4 or whatever it takes on your machine to get that constant reference. And of course, last resort, you can just type in those dollar signs. Let me make this bigger. Dollar signs around the column. That will make that a constant reference to F4. Okay? And then in Excel, if you have parentheses around your answer, that means it's a negative number. This is below the mean, right? Mean is 490. We're below that. $65.80 below the mean. That's the deviation from the mean. Okay? And then we can just double click this little square in the lower right hand corner, and that will fill our data set down. It's an ordered array. So one of our rents is $490. That's 80 cents below the mean. The next one is $500, which is $9 above the mean and 20 cents. Okay, so these are the deviations from the mean. The highest rent is $124.20 above the mean. And the lowest rent we already looked at, $65.80 below the mean. Okay. So we'll calculate these other things later when we get to them. And that's what, so it's all in the template. We'll do that later. Where am I? Okay, so this is another case where you need to be doing this stuff with me because you'll be uploading your apartment rents data with your calculations done. Okay, so the next thing we have here is a weighted mean, and this lets you assign specific weights to the different values that you're averaging. So this is what we do to calculate grades, right? You know, on the syllabus, which I don't think I have. Oh, maybe I do have it open. Yeah, I do have it open. Huh. Here's our weights. Right. 12% will be applied to your score for in-class work, or the participation score. I forgot to change that on the revise. But that's the participation score, 12%. Homework, 22%. So these are the weights, and they sum up to 100%. These are the weights. So weighted average would be, for instance, the in-class score, the participation score will be weighted by 12%. So I have 0.12 times that grade, and then I'll add the homework score, 0.22 times the homework grade. I'm adding to that, right? Plus I is equal to 1 through n. So I have weight I, weight 1 times score 1 for the in-class, weight 2 times score 2 for homework. I sum that up and then divide over the weights, which is just 100%, or 1 if it were in decimal form. I have to get grades in, so I'm going to shorten this video pretty quick. But quick example, here I have some 26 repair projects, and I want to get the weighted average days to completion because it's a frequency distribution I have. So I can do the weights. So weight 1 times the number of observations, the frequency in that took 5 days to repair. And so that's what I'm doing. I'm just taking the cross products here, days to complete times frequency. So the weight is the days to complete, that's our weight on the frequencies. So on our weighted mean of days to complete is 6.31 days. Okay, so that's a weighted average. You can do the same thing with grades. So here I have some grades. Here's my contributions from a different class. Probably Eco 252. Sum to 100, these are my weights. Let's say I got these scores on those parts of the class. 88% on in-class work, 79.5% on homework, etc. So to get my final grade in that course, I take a weighted average. And this will be the same thing I'm doing for you. Well, I was talking about these before, I wasn't showing them in the video, sorry about that. This is off the syllabus. So these are the weights, sum up to 100. So I'll be doing the same thing when I calculate your final grades, right? So grades times the weight, sum those up across all the grades, different types of grades, divide by the weights. I get a weighted average score of 87.18%. So it looks like a B+. I get a B+ in stats too. Okay. So I'm going to leave it at this. I'll add to this later. It'll be a little bit after our official class time, but I'm going to count it for today's class anyway. I want to get through at least the measures of central location today. But I have to get the grades submitted right now. So I'll stop the video here.